We have talked about pressure in the sense of what it does and how it relates to force, and even some of what we can do to use it to do other things. But we haven't really talked about where pressure comes from, so that's what this is going to be about. If you have gone swimming, you know that if you are jumping into the water, there's a moment where you go pretty far underwater and it feels like there's more pressure. Your ears might try to pop, but then when you come back up out of the water, then everything's okay. The difference is the pressure from the water above you. So what we are looking at, the farther down in the water you go, the more pressure you feel. If we were swimming in something other than water, we would end up with more or less pressure. So we need some kind of a formula, right? We're going to first look at the weight of the water that's above you. If I consider right here, you know how in the ice they drill these cores, or they drill these samples? Let's think about a core sample of this. This thing's got an area of A, and it's got a height of, well, if we are D below the surface, a depth of D below the surface, then there is a height of D, which means the volume of this kind of core sample would be area times depth. Now we know density is mass over volume, which means mass is density times volume. So the mass of this thing is going to be density times volume equals density times area times depth. That's mass. We are ultimately trying to get to pressure, and pressure deals with force. So let's think about the weight of this column. The force exerted by the column is just mass times gravity. So now we are at rho g area d. That's the force. But the pressure, that's a force over an area. So if I go right here and erase this and set this up, my pressure is force over area. Area and area cancel, and I get this equation for depth pressure, and it is rho g d. If I am farther below the surface, then the depth is greater, and I end up with a higher pressure. It doesn't matter whether there is more stuff going on to the sides. What matters is what's going on directly above. And it's because that area is going to cancel out, is going to be divided out. Now there is one more issue. Anytime we're in the water, here on Earth, if we are right here at a depth of D below the water, there is still the question of, is this all the pressure that we deal with? And this isn't societal pressure or emotional pressure. This is just, is this all the pressure we deal with? And the answer is no, because above the water we have the air. Air pressure at sea level is 1.01 times 10 to the 5th pascals. But most of the things that we deal with, most of the problems we do, are somewhere near sea level. So when we are talking about a depth pressure, a lot of the time we want a relative pressure, not an absolute pressure. The idea with relative pressure is how much is our pressure different at this point versus at the surface. At the surface we still have that air pressure. So when we do like a depth pressure we are talking about a relative pressure. We are saying what is added because of the fluid that we're in. That's it, really.